the water depth is 4 feet. It looks like these 3 points all fall on a line, so maybe the function we are graphing is linear. We can verify this mathematically by calculating the slopes of the line segments connecting the first and second points and the second and third points. If the slopes of both segments are the same, then all 3 points must lie on the same line. As we saw in the chapter on slope, we can calculate the slope of a line which passes through 2 points as the difference in the point's y-coordinates, delta y, divided by the difference in their x-coordinates, delta x. Dividing delta y by delta x, we get -4 over 3, or a slope of -4/3. Now let's calculate the slope of the other line segment. Once again, we take the difference in the y-coordinates, delta y, and the difference in the x-coordinates, delta x. Dividing delta y by delta x, we get -2 over 3/2. We can simplify this complex fraction by dividing -2 by 3/2. This is the same as multiplying -2 times the reciprocal of 3/2, or 2/3. -2 times 2/3 is -4/3. So the slope of this line segment is also -4/3. Since the slopes of these 2 connected line segments are the same, all 3 points must lie on the same line. We can therefore assume that the water in the pool is draining at a constant rate and that the water depth as a function of time is linear. Since we know this line's slope and at least one point which falls on the line, we can write the equation for this line using the point-slope form. If we choose the bottom point, which has coordinates 6, 4, to use as the known point in the point-slope formula, then x1 is 6, y1 is 4, and the slope m is -4/3. Now that we have an equation which represents water level y as a function of elapsed time x, we can plug in different values for x to see what the water level will be at those points in time. For example, an elapsed time x of 0 corresponds to the time when the drain was first opened. If we set x to 0, then the resulting value of y will tell us the initial depth of the pool. Completing the arithmetic, 0 minus 6 is -6, and -4/3 times -6 is +24/3, or 8. Adding 4 to both sides of the equation allows us to cancel -4 on the left, leaving us with y equals 8 plus 4, or 12. So the initial depth of the pool when the elapsed time x was 0 was 12 feet. If we would like to find out how long it will take for the pool to be empty, we can set the water level y to 0 and solve the equation for x to see what the elapsed time is at that point. We start by setting the value of y to 0, and we can then write 0 minus 4 as -4. Since we are trying to find the value of x, we want to rearrange the equation so that x is alone on one side. To do this, we must first eliminate the -4/3 by multiplying both sides of the equation by the reciprocal of -4/3, which is -3/4. Since anything multiplied by its reciprocal is 1, we can replace -3/4 times -4/3 with 1. Now, since everything in the parentheses is multiplied by 1, we can eliminate the 1 and the parentheses. Completing the arithmetic on the left side, -3/4 times -4 is 12/4, or 3, and adding 6 to both sides allows us to cancel the -6 on the right, leaving us with the equation 3 plus 6 equals x. Adding 3 and 6, we have 9 equals x, or equivalently, x equals 9. So when y is 0, x is 9. Since x is the elapsed time, and y is the water level, this result tells us that when the water level y is 0, the elapsed time x will be 9 hours. Since the drain was opened at noon, the pool will not be empty until 9 o'clock.
Excuse me, Professor von Schmohawk. Did I just hear you say that my pool will not be empty until 9 o'clock?
Yes, Professor Etheline.